good. So yeah, the title of this presentation is From Binary Prediction to Real-World Problems. And the reason is that binary prediction doesn't exist anymore. So spam was possibly the last binary prediction problem in the world. It's considered solved, and so is binary prediction. Thanks. Okay, no, I'm just kidding. So what I'm actually going to talk about is AI or machine learning in the old days. Right? So this is a machine built by Martin Riedmüller. He joined Google DeepMind recently. And this machine, I have to start it perhaps. Probably it's starting now. So this machine is a card pole balancing machine. So perhaps you have seen something like this before. So there's this pole over here, the blue pole, and this machine can move the card with actions to the right and to the left. And the goal of the machine is to balance the pole upright. Right? And now the machine is learning how to do it without any prior knowledge. So it's exploring the state space, it's moving the cards randomly to the right and to the left. Not very successful in the beginning. But we'll see that it's getting better and better. So this is after 25 tries. So the machine is actually a mechanical device. It makes a lot of noise. I turned down the volume. So I think it's kind of interesting to see what a machine does if it wants to learn something from scratch. It's also kind of boring because not a lot of things happen here. But I see that it's making progress. Perhaps it's overdoing it a bit, but see, it's working out, right? You can find the video on YouTube also. But it's not that bad, it's not perfect yet, so you will see the final controller, not even yet, but in the episode after this, there's the final controller, and this is also robust. If you put some noise on the pole, then it will equalize it. I think now is the last one. So it's pretty good. There's, I think, Martin coming and putting some noise into the system. Not bad, isn't it? So it's actually a great piece of science and completely ridiculous at the same time. And so this is what AI or machine learning used to be. And then there was something that we call digital transformation and digitalization and digitization. Just to have all of us on the same track, I will briefly tell you at least my notion of this, and then we move on to the final. And I will use 3 examples for lack of time, perhaps I only skip through them. So it's classical long players. I'm not sure what you guys are. I, at least in my youth, I was using long players. Then we have money, represented by this funny pig over here, so cash, and newspapers. Right? And in English, you would differentiate between digitization and digitalization. In German, we would translate both with digitalisierung. But the digitizations, that means that we digitize the medium. Right? The data is being digitized. We don't have an analog long player anymore, but now we have a CD. Right? We don't use actually cash, but we can pay with a credit card. And the step afterwards is then digitalization. And now technology changes industries, right, by digital processes. So we don't need to have a CD player anymore, but we can use an MP3 player. It's much smaller and we can carry it around wherever we want to. It's much more convenient. We also don't need to turn on the TV to read Bildschirm text anymore. Right? We can now turn on the internet and access the news from wherever we are. Finally, digital transformation. Now, again, a disruptive thing. We don't need everything that I told you before. But we only need Spotify and stream everything directly into our electronic device, whatever it is. Right? We don't need to open news archives, read newspapers, or check news online, because if we have a Twitter account, news will come to us. I don't need to do anything. Right? If I'm on the right channels, then everything just comes to me and done. And last year, for instance, every minute of the day, users generated 187 billion emails per minute, right? Or issued 3.7 billion queries at Google. So users viewed 4.4 billion videos, or sent 38 million text messages per minute, every minute last year. Right? Also, the money spent online increased again. So now we are at about $850,000 per minute that is spent online, and we have about 1 million Facebook logins every minute. Of course, these people will log off because nothing happened, but in the next 10 minutes they will relog in. So we are creating a lot of new data, and actually in April 2015 and also now we are creating at least 2.5 quintillion new bytes every day. So this is a number that you cannot imagine anymore. At least I cannot. So if you burn this on Blu-ray discs and you stack them up another, you will have the height of 4 Eiffel Towers in Blu-ray discs. So that is 90% of the world's data has been created in the last 2 years. Right? Data has become an asset. It's growing much, much faster than the world economy. So if you have data, you are somewhere. Somebody, not somewhere. You're probably also somewhere. Right? So data means a lot. This will in principle go on. And I would like to give you an example of where data also appears that you may not have think of. It was a long day, sorry. So this is positional data of football players. So we have XY coordinates of every player in the ball. The DFL is recording this regularly in the first and second Bundesliga. You have a ball possession indicator that tells you which team has the ball, and there's also an event log that tells you what's going on. So they're annotating shots, fouls, goals, of course, corner kicks, and so on. So we use this data and ask the question, what is the player going to do next? So can we predict what all the players are going to do in the next 2 seconds? So for instance, the ball is over here. You see these tails of these blue and red dots. Blue is playing red. So the tails mean this is the positions where they were in the last, let's say, couple of timestamps. So the longer this tail is, the faster they are running. And for this guy, the encircled guy in red, we computed a couple of predictions, shaded in green, with different confidences. So the number, the higher, the better, is what the machine believes where this guy is running in. And here we would probably say that the dark green point is the next location of this player, and actually the player went to the red. How do we do it? We use reinforcement learning. So we translate this game into a Markov reward process, where we have a state space of all the positionings of 22 players and the ball is a state. And then we have a transition from one state to another, because we don't have continuous measurements, but we have timestamps. So data is usually recorded with 25 frames per second. So the transition from one frame to another is a state transition. And then we compute movement policies for agents. So what is every agent going to do? And every agent is coupled, or let's say connected, with all his teammates or her teammates by a collective reward. And the reward is high when they win, or when they reach from a collective goal. And it's 0 if they fail. So what we then usually do is we learn a value function. I don't want to go too much into details. I just learned that I only have 50 minutes instead of 25. But I'm quite good in time, I think. Yeah. Okay, good. So just to give you a broad idea of how it's working. So we have some Gaussian mixture model that are actually that generates us these predictions. And then this is like probabilities drawn also from this mixture model that say how likely is it that this point is being generated from this component or from that component. So since we only learn from observations, right, from real games, we don't simulate. Usually you simulate in reinforcement learning, we don't. And we learn a value function for the observations that we have. But that means that everything else cannot be explained by the model. We only can explain what we saw in the game. So therefore we need to generalize this value function to everything that may happen. And then we plug it. So this is like we turn this into some kind of loss function or error function. And then we plug this into a deep architecture and optimize it. So the idea is that every layer is a slice through the entire network, which you could use as an embedding layer, if you like. So we have 12 input channels. So we have the positions of one team, the positions of the other team, the position of the ball, the velocities and directions of movement for these three also. Ball possession, size of pitch, and location of ball. Size of pitch was important because players were running out of the pitch at some point. Now they don't do this anymore. Okay, and now the nice effect that we see here is that if we draw a lot of possible movements from this model, we get something that we call a movement distribution or a movement model. So this guy, the red guy, is standing. It's not moving at all. So this person has the chance to run in almost any direction equally fast because there's only the time needed for turning around and then speeding up. So it's a spherical isotropic distribution of points, while this person over here, so all the points laid before, it's more like an ellipsoidal shape. Right? So the model is pretty much convinced that this player will probably move to the front and will not stop and turn and run backwards. So this is just by observations. We don't have any prior knowledge of movement, but it makes sense. And it's individual movements. So if you have one player who will, in this situation, always stop and run backwards, then this player will also have points behind him. And then for evaluation, as I would like to show you a movie in the end, we compute a lot of these points, not so many, we only compute 4 or 5 points, and then we take the best one. And we do this for all the players. And from these players that are projected into the future, from the locations in the future, we apply the movement models that we inherently learn also in the model, the ones that you just saw. And we compute which point xy coordinate can be attained by which player fastest. And this gives us something that we call the control zone of this player. For this player, for instance, we assume that the player runs to this position. We compute the position in the future for all the other players, apply the movement models, and then we say all these points in this orange area can be reached by the red player quickest because he will be here. This kind of making this slightly complicated story very short. So hopefully we have it. And what I show you now is a game from the Euro 2017, the Women Euro. It's I think the gray team is Norway and the blue is the Netherlands. The Netherlands won in the end. Okay, for some reason I cannot stop the movie now. Okay, then I explained before what you will see and then I show you. So you see there's a throw-in, the red is the ball, and then they play the ball a little bit in the midfield. And this player here sneaks away from her. And in the future, Oh, sorry, I forgot to say something very important. So the positions are now in real time, in our time, but these areas are projected into the future. So the areas are the variables or the control zones in the future of these players. So you will see that she will create a zone in the future that reaches the box. And then the ball is being passed in exactly that position. Then there's a one touch, she just crosses the ball. And on the other side, the winner on the left-hand side, in that moment creates a zone that is like reaching the 5 meters, area, and then directly scores. Okay, now the movie. And now they are playing the ball back and forth. And now she sneaks away, right? The zone is super large. She gets the ball and then passes directly, and the other girl also tries to score directly. So in the end, the model very well predicted what could happen. Right? It's not what is going to happen, but what could happen. And then, because we can compute a lot of things with this model, we can also come up with some ranking, and we see that that the top-ranked players kind of are well aligned with newspaper rankings and everything else. I have a shameless plug because we also published a book on sports analytics. And another shameless plug because I'm organizing the ECML conference in Würzburg this year. So if you don't have plans for September, you are very much welcome and cordially invited. And now the take-home message. So machine learning as it was, machine learning as it is today, is still using the same methods, process reinforcement learning. And what we did here has probably not been possible without that. So this is a plea for basic research. So go to the universities, guys, and learn something. Okay, this is it. This is my group. Thank you for your attention.